Good afternoon, students. As we know that we have completed only first three units. Now we have to complete unit 4, 5 and 6 because of coronavirus. Due to this, uh, as it is not possible to complete in college, so we will complete it through videos. Now I am going to start our fourth unit. This is nothing but the flow through pipe, or we can call it as a internal flow. Now in this unit we will see the flow of fluids which are viscous and flowing at very low viscosity, low velocity. Okay, as you know that at low velocity fluid moves in a layers, and each layer of fluid slides over a adjacent layer, and due to this relative velocity between layers, the velocity gradient du by dy exists, and hence we know that from first chapter or from Newton's law of viscosity, the shear stress is directly proportional to this velocity gradient du by dy. So to remove this proportionality constant, we need one constant, and such constant is called as coefficient of viscosity, this nu. So as we know that from second chapter we studied the various types of flows, in which we have studied laminar flow and turbulent flow. As we know that in laminar flow, the fluid particles move along a straight line or a straight parallel path in layers or lamina, such that the paths of individual fluid particles do not cross these neighboring particles. But when the velocity is increased or fluid is less viscous, the fluid particles do not move in a straight line. The fluid particles move in a random manner. Then the resulting fluid motion is called as turbulent flow. So a laminar flow changes to the turbulent flow when the velocity increases. First point, when velocity increases. Second point, when diameter of the pipe increases. And third pipe, when the viscosity of the fluid decreases. So these three parameters are responsible to changes from laminar to turbulent. But the Reynolds was first to demonstrate that not only mean velocity but a quantity rho v d by nu is responsible for the transition from laminar to turbulent, and this dimensionless quantity is known as Reynolds number. So if this Reynolds number is less than 2000, then the fluid is said to be laminar, and if this Reynolds number is greater than 4000, then the fluid is said to be turbulent. Okay, and if this Reynolds number lies between 2000 to 4000, then we can say that the flow changes from laminar to turbulent. Okay, so now this chapter deals with the flow of fluids which are viscous and flowing at very low velocity. Now the following cases will be considered in this chapter. First one is flow of fluid through circular pipe. First one is flow of fluid through circular pipe. Second one is flow of fluid between two parallel plates. And third one is kinetic energy correction and momentum correction factors. So this chapter deals with these three phenomena. First one is flow of fluid through circular pipe. Second one is flow of fluid between two parallel fixed plates, and third one is kinetic energy correction factor and momentum correction factor. Now we will see the flow of, we will deal with the first subtopic, such as flow of fluid through circular pipe. Okay, now for the flow of viscous fluid through circular pipe, we will determine the following four parameters. So for this case, we are going to find out four parameters. First one is shear stress distribution. Second one is velocity distribution. Third one is, first one is shear stress distribution across section. Second one is velocity distribution across section. Third one is the ratio of maximum velocity to average velocity. Okay, and last one is the drop of pressure for given length. Means delta P. Okay, now we will consider, or we will determine the first term, that is the shear stress distribution across the section. Okay, so consider a horizontal pipe of radius r. So consider a horizontal pipe of radius r. So the radius of this pipe, this is diameter and this is your radius r. So consider a horizontal circular pipe of radius r. The viscous fluid is flowing from left to right. Okay, the viscous fluid is flowing from left to right. So now consider a fluid element of radius small r. Consider a fluid element of radius small r. This is the center line of the pipe. Now consider a fluid element of radius r. This is the radius of this cylindrical fluid element. Okay, let the length of this fluid element is delta x. Okay, now if P is the intensity of pressure, now these are the faces A, B, C and D. Now if P is the intensity of pressure acting on face AB, then suppose this is the P, intensity of pressure acting on face AB, then the intensity of pressure acting on face CD will become P of x plus delta x. Now this P of x plus delta x can be expanded by using Taylor series expansion as P plus dou P by dou x into delta x. Okay, so the forces, now we will consider the forces acting on this cylindrical element. So first one is the pressure force acting on face. First one is the pressure force F acting on face AB, which is given by the formula pressure on face AB into area of the face AB. So pressure on face AB is P into area of this face is nothing but pi r square. Similarly, force acting on the face CD, which is nothing but FCD, which is given by formula pressure on the face CD into this area, same area will be there, pi r square, which is nothing but PCD is nothing but P plus dou P by dou X into delta X. So P plus dou P by dou X into delta X into pi r square. Next force is due to the shear stress. Next force is due to the shear stress tau. Okay, now the force due to shear stress is given by this tau shear stress into this circumferential area. Now this circumferential area is nothing but circumference of this cylindrical element into the length of this cylindrical element. Now circumference is 2 pi r into length is delta x. So this shear force or force due to shear stress will become tau into 2 pi r into delta x. Okay, as there is no acceleration, the summation of all the forces in the direction of flow must be equal to 0. So if we take the summation of forces in x direction to be 0, we will get first force acting on face AB, which is acting in right direction, so it will be positive. So P into pi r square. Next force is the force acting on face CD, which is acting opposite to the face AB, so it should be negative, minus P plus dou P by dou X into delta X into pi r square. Then third one is the shear stress which is acting opposite to the motion of the fluid. As the motion of the fluid is from left to right, so shear stress will act from right to left, so it should be also negative. So minus tau into 2 pi r delta x, and the total addition of the forces should be 0. So from this we will get, now simplify the equation, P into pi r square minus P into this pi r square minus dou P by dou X into delta X into pi r square minus tau times 2 pi r delta X is equal to 0. Now this will get cancelled to this, so finally will become minus delta P by delta minus dou P by dou X delta X into pi r square minus tau into 2 pi r delta X is equal to 0. So finally this delta x will get cancelled because it is common. Similarly this pi will get cancelled because it is common. So finally it will remain dou P by dou X into r square minus 2 times tau into r is equal to 0. This r and this square will get cancelled. So finally it will become minus dou P by dou X into r minus 2 times tau is equal to 0. Okay, so finally we need the shear stress distribution. So minus 2 times tau is equal to dou P by dou X into r. Therefore shear stress distribution tau will become minus dou P by dou X into r by 2. So this is the final shear stress distribution across the section. So from this expression we conclude that this shear stress is directly proportional to the radius of this cylindrical element. So which means that This shows that the shear stress across a section varies with radius r as dou p by dou x across the section is constant. Hence, the shear stress distribution across the section is linear, which is as shown in figure as if this is the flap section. So shear stress distribution is linear across the section. This will be the shear stress distribution. So what does it indicate? Shear stress is maximum at the wall section and it is 0 at the center of pipe. So in this way we have found first parameter like shear stress distribution, and in next video we will go through velocity distribution, or we will find out the velocity distribution across the section, then the ratio of maximum velocity to average velocity, and finally the drop of pressure for given length. Okay, thank you.